Peter Hughes is going to come up and he's going to share with you sort of from the perspective of a chief technologist. And I'm not exactly sure all of the slides, but he's pretty amazing. Peter has actually been a champion of NASA iTech since we started it.
And still am.
And going into an agency, being that little girl, going into an agency new, you need support. You need leaders within an agency to actually help support you to build something like we've built. And you know, Peter was one of those people. And so he's going to share with you some things today, but thank you, Peter, for always being a champion for what we're doing.
Thank you for hosting me today.
Please welcome Peter.
Good morning, everyone. So yesterday, you engaged with a number of my colleagues, the Center Chief Technologists from 4 other centers. Today, I'm here to present an overview of what I do as the Center Chief Technologist at the Goddard Space Flight Center in Greenbelt, Maryland. I would have liked to have been here yesterday. Unfortunately, yesterday was a big event for my program at Goddard Space Flight Center. It's the day that we have our technology IRAD, Internal Research and Development poster session, where I have 130 PIs stand up in front of their posters and interact with each other and share with customers and stakeholders and new partners some of their results and trying to understand how we could apply these technologies, how to better apply these technologies and infuse it into missions. I also gave out the Innovator of the Year award to Dr. Michael Kranak, who's been active in lasers for a very rich 30-year career. Taking these technologies and innovating it in new ways, whether we're using these lasers for altimeters or looking for species in the atmosphere for science measurements. He's also always stretching the boundaries, identifying new technologies like femtosecond lasers, where we're using lasers at very high speeds to be able to weld together 2 dissimilar materials. But he's doing this in a way not just at the Goddard Space Flight Center. He's doing it with researchers throughout the community. He's working with labs, he's working with early career folks, he's working with students to develop these technologies so they're ready to take on next generation mission opportunities. I also presented a team award to the Dellinger team, a team that's been evaluating small sat technologies, understanding how we use this technology for next generation measurements with this small platform that is really taking the remote sensing community by storm. We learned a lot from that, but it's led us to an opportunity where we better can use this technology to make these measurements from low Earth orbit for a fraction of the cost we originally we did with the larger platforms. This morning, I'm going to spend about a half hour with you to share with you what we do at Goddard Space Flight Center. I'm going to go over a subset of our portfolio, our mission portfolio. And then I'm going to share with you some of these technologies we're investing in and some of the emerging technologies to showcase some of the things we're interested in continuing to get engaged in to help make our mission for exploration and scientific discovery very productive. So yesterday you heard from my counterparts at Langley, Stennis, Ames Research Center, and Marshall. And those 4 centers represent and are active in other areas in propulsion and aeronautics and information technology, some of the testing of the propulsion system, and preparing our astronauts for their space journey and managing the International Space Station. We at Goddard Space Flight Center in Greenbelt, Maryland, primarily focus on robotics spacecraft, and we also do some work with HUMD and some other emerging technologies. As you can see in this chart, we're primarily focused on discovering new science findings and translating that so we can understand how the origins of the universe occurred, what's going on with our Earth planet and other planetary neighbors in our solar system, and being able to develop next generation technologies to carry these out and also to help with our venture further away from Earth onto possibly a gateway platform near the moon, operating on the moon, and then beyond to Mars, and hopefully even further. Next slide, please. We are a community of about 10,000 people, about 3,000 or 4,000 civil servants, and the balance are contractors, primarily scientists and engineers with high degrees. We take great pride in doing a lot of work hands-on within our center to develop the instruments and the missions and carrying it on to execution. Next slide, please. We have 5 sites. The primary center at Greenbelt is where the majority of the people live and operate. And we have the Wallops facility where we do launch and suborbital platforms, where we now are launching to the station on Antares. And just last week, we signed an agreement with Space Labs from New Zealand to launch small sats and new platforms to space with a private venture from New Zealand. We do some earth science research at the Gist Institute in New York City. We also provide some validation of our codes and the data, the IVV facility in West Virginia, and we connect to our spacecraft through through White Sands ground terminal. I'll let you take this. Next slide, please.
Is it working?
It's not. I don't know if I'm pushing hard enough or what. So, as I mentioned before, our primary focus is as a science center, developing these instruments, mission concepts, and mission, and taking them for the full life cycle. Sometimes we do these missions in-house. Sometimes we partner with outside companies and we outsource the platform or various elements. Sometimes we are just executing the mission as a system engineer or project management. Another main area in the lower left-hand corner is the communications. We at Goddard take great pride in providing the communication infrastructure and have really helped with the infrastructure for about 98% of the data from the space platforms all the way down to its target source. We are a launch facility supporter from the Wallops Flight Facility. We've been doing sounding rockets for years, hundreds of sounding rockets. We also support the balloon development to take payloads to space for development of technologies, but also to take critical science measurements from that vantage point. And I mentioned we had the IVMV, and we're committed to understanding this data and make scientific conclusions. Next slide, please. You can go 2 slides ahead. Go ahead, I spoke to that already. One more slide, please. We structure our business around these 4 primary science areas at the top, the astrophysics, heliophysics, earth science, and planetary. I'm going to give you a glimpse of 4 of those mission sets, what we're doing at Goddard, and a glimpse in some of the technologies that are going to lead to next generation missions in these areas. We also we have a pretty robust cross-cutting technology program. And with this, I look for technologies that may be emerging, they may be nascent, that may cut across, span across multiple of these lines of business that bring new value and bring new capabilities to enable that next generation set of mission set. We have a small portion of Goddard who's supporting HUMD in the area of supporting with its scientific instrumentation, but also in satellite servicing, which we've been active in ever since we serviced the Hubble Space Telescope. We've had 5 very successful servicing missions to restore the grandeur and the capabilities of this magnificent space vehicle. And we're looking at taking that to the next level for next generation servicing of platforms in space. And so we could better understand also how we could live and we could construct very large structures in space with partners throughout the industry, also with some of our sister centers. Before I go into detail on some of our missions, I just want to start briefly with a little story. Being at Goddard, I was very immersed in the robotic spacecraft for years, and I had the opportunity about 10 years ago to go see my first shuttle launch. It's an experience that should not be missed by anyone. And I actually was allowed to bring my family. I paid for them, of course, on my own dime. And we were up on the observatory deck, steps away from Charlie Bolden as we counted down together in the night sky, 3 o'clock in the morning, with a crowd just exuberant around us, counting down with the energy of this magnificent vehicle that was about 2 miles away, getting ready to launch into space. When it lifted off in space, the crowd's noise dimmed to a whisper. And I look to my side, and Charlie Bolden's right there. My kids are by my side, and they're up looking at him because tears are streaming down his eyes. You know, he's just so proud of this vehicle. And I noticed the astronauts' families that are surrounding me also were really quiet. This astronaut wife was just praying, saying, please, please, please. So here we are taking one of the most complex vehicles, lifting into space, and with one of the most precious things on Earth, and that's human life, to deliver to space so we can live and operate on this magnificent station. We've been living there for continuously nearly 20 years, doing groundbreaking science by our astronauts and cosmonauts that we send up to this platform, so we can better understand how we could live and operate in the zero-G environment, and to better understand how the human system performs and how our electronics and our missions will operate there. When you go on the street and you talk about NASA, most people think that's the main thing we do. They think almost exclusively that's what we do. But we do so much more than that. We're looking to take humans off this planet to go to other planetary bodies so we can explore. We've been exploring for a while, and this is exactly why right here. This is a child, very inquisitive child, trying to get right next to what he's interested in and trying to get more data, to touch it, to feel it, to see if it scrapes off. And this is exactly why we send these rovers and we go do in situ science at these planetary locations. Here's MSL. We have a very important payload on there, SAM, Sample Analysis at Mars, where we're actually roving across the surface of Mars, taking scoops of material, looking for signs of chemistry that may have proven organic existence, or that there may be signs of water, significant signs of water. It was launched 10 years ago, and it really is opening our eyes to science on that planet. We also launched OSIRIS-REx 2 years ago with our partners from a university. So we could send this spacecraft to an orbiting asteroid. It's going to rendezvous with Bennu, this asteroid Bennu, in about 2 months, or later this next month. And it's going to, for about 500 days, going to be characterizing that asteroid and trying to assess what's going on at the surface level, characterizing materials on there, and trying to determine where we're going to go down, make a real close pass, or really close proximity touch, and actually suck up some material. We want to grab about 6 grams up to 2 kilograms of this material and return it to Earth about 2 years later. But we do more than the in situ science. We've been doing remote science for years. One of our flagship missions, the Hubble Space Telescope, is something we're quite proud of. We're about to celebrate our 28th anniversary. Actually 29th, I guess it is, this coming April. That's been up there in orbit, 300 miles above the Earth, making discoveries that has transformed our understanding of astrophysics. This vehicle is just magnificent. Granted, we launched it, we had some engineering problems with it, with the optics. We were able to correct that. And thankfully, because it was a serviceable vehicle, serviceable platform, we were able to send up astronauts up there and change out some of our instrumentation to modify so it would be productive. And since then, the science that it's delivered is absolutely spectacular. The science community really has whole new insights into the age of the universe and the galaxies and the surrounding bodies that are around us, and better understanding dark energy that's propelling the expansion of the universe. It also had all kinds of remarkable discoveries. This is one really widely known science experiment where they took the vehicle and pointed into a really small space in the sky by Ursula Major. And we're talking a very, very fine point in the sky. I mean, if you imagine those coffee stirrers you might be able to get from McDonald's with a tiny little hole in it if you look through it, but not at eye distance. If you took that stirrer and held it out at arm's length, and we're talking 122 arc seconds out in this part of the sky, and we just stared. And there's just a few objects and a few planets in our galaxy that you could see, but we let it collect more and more light over a number of minutes and over a course of days. And it revealed this complexity of objects deeper into space. These objects are galaxies. They're some of the individual bodies, but these are individual galaxies further out of various shapes and sizes and ages. And we've learned tremendous amount about these galaxies that are further out there. and we want to explore more. We want to use the next vehicle, the James Webb Space Telescope, that's going to be able to peer through the dust using different wavelengths to better understand what's going on in there, what the dynamics are of the creation of those planetary systems. This is a new mission we've been working on for about 18 years or so. We're looking forward to being able to launch it within the next few years. We've had tremendous challenges here and there to try to get this vehicle ready, both throughout the project team and with some of our partners. But it is a very complex vehicle with a very large primary antenna made of aggregation of these individual mirrors about 1 meter across, these beryllium mirrors that we drilled out the back of them to lightweight them. We coated it with gold and made them super smooth so that there's no aberrations there. We have this huge sun shield about the size of a tennis court, 5 layers thick, that's trying to protect the optics from the heat of the sun. There's very advanced instrumentation that's going to be on the warm side, but there's challenges with this mission throughout. First of all, to launch it, we had to fold up the entire platform and be able to fit it into a launch vehicle that's much smaller. You can see through this animation where we're opening up the sun shield. We're going to expand it and to protect it from the warmth of the sun. We also had to take the optics that were folded together and put it up into one big array of the mirror. And we're going to be able to adjust all those mirrors so it appears like it's one big mirror that we could operate on and collect a lot of light over a very long stairs. I'm not going to go through this whole video out of the interest of time, but you can see as we go through these steps in the initial days and weeks, as we unfurled this magnificent machine, test it out and put it out in its orbit, that it's going to be able to do really transformative science. Next slide, please. Because this spacecraft is not going to be 300 miles above the Earth, 400 miles above the Earth like Hubble Space Telescope. It's going to be in a location behind the Earth, about 1 million miles, in the L2 orbit. So imagine, instead of orbiting every 90 minutes like Hubble does, it's going to be 1 million miles behind us. So it's 90 million miles from sun to Earth. It's going to be 1 million miles behind us, orbiting the sun once a year, just like the Earth. And from this vantage point, it's going to be much colder out there. We're not going to have heat from the Earth. And we also we don't have the Earth to occult us at any time. Because you can imagine the Earth right now with Hubble, a good portion of the sky is occulted by this big body that we're next to. Very big challenges along the way. We had a number of technologies that the JWST-12 technologies that we had to get up to a certain technology readiness to be able to prepare itself to make sure it operate and as we planned. It's been a big challenge for us at Goddard through our partners, but we're learning a lot about these technologies, and we are confident now that we're going to be able to launch this magnificent vehicle, this new time machine for next generation astrophysics discoveries. We're doing other astrophysics missions, of course, too. At any time, we probably have a portfolio of 3 to 8 missions or instruments that are active at Goddard. We're in the final stages of the NICER mission, the Neutron Star Interior Composition Explorer that was on station. It's about the size of a big wash machine with 56 of these concentric X-ray mirrors. They're collecting data, looking at these neutron stars, staring at it, trying to understand what's going on with this body in space. But we're also doing something else, and I don't have a slide on here that actually spells it out, but the Sextant mission, where we're using these pulsars that we know that are unique timing devices that are very accurate in timing, so we could use it to better get this timing down and have some algorithms that we could possibly use pulsars as navigational beacons as we travel deeper into space. Very transformative technology. We appreciate the investments by the relatively new STMD mission directed in this technology area, and looking forward to how we can miniaturize this so we can have a much smaller platform for pulsar-based navigation. We also are active, as you can imagine, in earth science. Some people believe the only things we do at earth science and astrophysics, but it's so far from the truth. NASA has a very active fleet of earth science, Earth-observing satellites, some of which we've been involved with. Some of the most noteworthy ones are the ISAT mission, which we launched in the early 2000s, and in about 2003, I believe it was, and it observed the cryosphere, the ice at the global caps and on the land masses, and we observed it, really measured it very carefully over about 8 years. observing this significant loss of ice during this period. After the loss of the laser of ISAT-1, we wanted to have a continuity record, a record of a continuity. We actually started developing earlier than that the ISAT-2 mission, but there was this gap of years, so we had to have aircraft that took these measurements over those ice caps during this period of time. I'm pleased to say that just September we launched ISAT-2, a really magnificent follow-on to ISAT-1. It's got a very complex laser on it with 6 beams shooting out, like 10,000 pulses a second, having very accurate measurements of the surface of the ice, and also able, of course, to measure the land and other measurements too with this laser while it's in orbit. Looking forward to the discoveries from this beyond what we anticipated, beyond just the ice measurement, and it's that kind of unplanned discoveries that I think really makes these missions so great as we launch them into space. Goddard is also very active in heliophysics missions. We've partnered with a number of organizations for the STEREO mission, which we launched 2 decades ago, I think it is. And these are 2 spacecraft that are both in orbit around the sun, but at different vantage points. And trying to get a 360-degree observation of the sun so we could better model it and better predict when there's going to be coronal mass ejections and other scientific phenomena at the surface and beyond. These scientists are very eager to look at what's going on with the interior, the subsurface of the sun, and how it creates these coronal mass ejections where this energy gets burped out and it goes flying through space, these huge waves of energy that if you're unprotected, that it would totally wipe out your electronics, it would wipe out the humans. Fortunately, at our planet in the solar system, we are protected by a magnetosphere, protects us on Earth, it protects the astronauts that are close to Earth. But if they're further, they won't have that protection. We're going to have to prepare for that. We're going to better be able to prepare when these waves of energy are going to come and what we're going to do to protect them from that. We have a number of missions in this area. We've been involved in a handful of them and instruments both near Earth and out in the magnetosphere and better modeling this very dynamic area, better be able to predict both what's going on in the sun and how it'll react in our Earth system and other locations throughout the planetary system. We have a very big contingent of people doing modeling of these phenomena for the heliophysics. We do some of the basic code, some of the research code. NOAA is actually the operational space weather center. We develop some of these codes and new predictive models and actually feed them, so we call it research to operation, so we can increase the reliability and the accuracy of those type of models. So this is one of the slides that I'm most proud of, because this is a slide the entire Goddard Space Mission portfolio. These are all missions that we either delivered as partners or led the development of or have instruments or a major role in the 4 areas: in heliophysics, earth science, astrophysics, and planetary. Most people don't associate us with planetary, but we've developed the largest number of instruments that are actually taken to the planetary surfaces with our partners at JPL and Lockheed Martin and other places to make very wild discoveries in those planetary bodies. And we're looking forward to the next round of missions that are coming that are going to be offered, these announcements of opportunity from the Science Mission Directorate, which Dennis is going to talk a bit about at lunchtime, Dennis and Drusik. And we prepare for these missions using a very active IRAD portfolio to identify what the measurement's going to be, what the scientific mission would be, who we're going to partner with, and make sure we could execute that. For that, I have an internal research and development program where I put out a call internally to our scientists and engineers to identify what these missions are, what these measurements are, and what these instruments are. And we developed the tall item technology risk that will lead to that mission. We have numerous examples. I could go over hundreds, literally. On an annual basis, I award close to 100 of these, and about 25 to 40 actually get follow-on funding that's significant. Examples of these, you can see we have optics for X-ray mirrors. Both at Goddard and at Marshall, we both deliver exquisite X-ray instrumentation and optics. for this important wavelength. We deliver instruments of all sizes, and here's in the center, we have a microspec that we flew on an aircraft above the atmosphere, or at that very height, top part of the atmosphere, to validate this for critical measurements. We have all types of instrumentation that led to NICER and its execution, and we're investing in new technologies right now, particularly in lasers and quantum technologies and a little bit in radar, but mainly in partners outside. And we're using a number of these emerging technologies, including the advanced computing on board for the space cube that you see in the lower left-hand corner. Tom Flatley was proposing these ideas back about 15 years ago. At that time, no one was asking for this advanced computing. Everyone says we needed more, but no one was explicitly asking for this. And this is why we had to play a role of having the foresight to looking beyond the horizon and figure out what technologies we need and what missions they will enable. Some of the other technologies that we're investing in, we've been doing advanced navigation technology so we can have more autonomous navigation at our destinations as we move further away from Earth. We've been investing in a number of these small set-based technologies, but we are stepping away from the platform technologies and mainly focusing on 3 areas that I'll share with an upcoming slide. We've been very active in 3D printing as users of the 3D printers. And we partner with Marshall, we partner with Langley to develop whole new designs for the objects or the subsystem that we're designing in unique new ways, using new materials and folding together both the physical design, the electronic design, in new ways that allow constructs and compactness and efficiencies that we weren't able to achieve with the previous techniques. There's been a lot of comm technologies over the years. It seems like the bulk of the investments there are coming from the outside, from the commercial sector, and we're just trying to continue to miniaturize that for our platforms. And we're partnering with universities to use their facilities, such as atomic layer deposition and other techniques as these emerging technologies are taking foot. In the lower left-hand corner is one of the instruments that we've been developing where we're taking an advanced technique where we're channeling into silicon for a very miniaturized spectrometer and for a Michelson array. It's very interesting. We're able to take some of these technologies that were, the size of microwaves or even refrigerators previously on like Cassini and shrinking them down to the size of like a 3U space cube or a 1U space cube. Very transformative technologies enabling instruments from very small platforms. There's a number of technologies we're interested in that are emerging that I think have tremendous potential. And on this list, I just list 4 of them that we're investing in and we're partnering on. One of them, of course, is 3D printing of electronics and nanoscale device printing. We think this has tremendous advantage over the current techniques, which are very obvious that you could actually print it ourselves, and we could correct things quicker with a quicker cycle time. This technology is very much at its nascent, and right now we're mainly using it for conductive leads over unique size and form and shape. But we're looking forward as we're now actually able to 3D print instrumentation directly on the substrata and in different locations in the actual spacecraft or the instrumentation. Upper right-hand corner, you see quantum technologies, an area that is possibly one of the most transformative technologies I've observed in my career. And there's 3 main areas. There's quantum computing that's being led by industry and the research communities trying to understand how to use this technology for new codes to make new computation that we really can't even do now with traditional computers. The second area is quantum security. We're using quantum entanglement. We think there's a lot of promise with that. We're working closely with universities. Our colleagues at Glenn are leading that. We're working with them to try to apply that for greater security for our communications. And finally, the quantum sensors. And this is the area that Goddard is focusing on. We think there's tremendous value in this cross-cutting technology, both for astrophysics purposes, possibly being able to detect gravity waves, from planetary purposes, from being able to look for voids or other unique phenomena in the planetary surface and beyond, earth science, and trying to get extremely precise gravimeters for water moisture, or moisture in the surface of the planet, and other applications for like gravity, extremely precise gravity. In the lower left-hand corner, we have integrated photonics, the idea of using light as the medium within these little integrated circuits, integrated photonic circuits. This is going to be the next new wave in our electronics beyond what we have now in our electronics, and seeing the profound advances we've seen with the microelectronics over the last 30 years. We are very optimistic that this will be very helpful, not only for that we're going to be able to create circuits that aren't emitting heat for our miniaturized instruments, but we also believe that there's whole new ways that we can make our computing and laser comm subsystems a lot more compact. Finally, the whole world is taken by the rapid emergence and application of AI and machine learning. This technology has profound capabilities to transform how we manipulate the data, how we make conclusions of the data, and not only in our science mission, but I think it's really going to be transformative within our systems across all disciplines, but also within all functions within our industries. We're looking carefully at how to do this, and there's a movement to better understand how we can do this digital transformation. I believe it's an overused term. There's a lot of hype associated with that. I've admitted that we've kind of been using digital transformation for years at Goddard, and there's pockets of it we're very expert, but we're not looking beyond these projects and these stovepipes to try to understand where there's value, to try to digitize and be able to transfer and have new processes using the interconnectivity and also using the machine learning techniques on top of that. So I think that's an emerging technology. It has a lot of promise, but again, we're trying to understand how to go forward with that. Finally, there's the area of small sats. Within the scientific community and within the research community and even down to high schools, there's a tremendous energy around small sats and CubeSats, mainly the CubeSats. I'm a believer in the CubeSats. I think in some way it's a little oversold at times. I think it's a great entree into the space system arena for STEM. But we just see it as another platform in our full spectrum of missions that we are offering our science community. We do everything from the aircraft to the balloons to be able to validate and make new measurements with those smaller vehicles or near-Earth vehicles. And we now see that small sats are a great way that we could demonstrate technologies and have smaller instruments and possibly use them for new vantage points to complement the very large and exquisite platforms that we've been known for over the generations. At Goddard, we've been active in this CubeSat arena for a while. We've been active in the small sat arena forever, for our entire existence, our entire 58 years. We're now harvesting new science measurements through some of the much smaller instrumentation that we're able to put on these smaller platforms. And so I'm very optimistic that there's science that's going to be very transformative with it, but I will say that it is not the only measurement platform we're going to have. We still need the apertures. We still need some of the large power and propulsion to get to these locations and stay on destination that CubeSats may not be able to afford. There's three main areas I'm prioritizing within CubeSats within the Goddard community, and they've known this for the last 4 or 5 years, I think. In the lower left-hand corner, we're prioritizing miniaturized instruments that we can make more compact to fit into these smaller 3, 6, 12U platforms. We're also looking for components that we cannot buy that are much higher reliability, that may be novel in function to enable a unique mission. And finally, I'm looking to use these CubeSats as constellations or a collection of them. Maybe it could just be 2 for a function that we could not do with a singular platform. Examples of these distributed science missions are in front of us here. On the left-hand side, a young scientist had this idea of having a sphere covered with carbon nanotubes, that we could then have it in free space. And as it's floating, we can manipulate the second platform, a CubeSat, to use it as an occulter. We possibly could use this for solar occulting, or we could do it for planetary reasons, or exoplanet possibly. But we're trying to use these 2 platforms dynamically and adjust the maneuvering of this so that we can make these alignments. We've had a number of activities in this, both internally through early concepts, but also we did a recent proof of concept with some partners in South Korea, taking a number of technologies throughout the industry and real quickly getting this on orbit and having this astrometric alignment for other reasons for this, what we call a virtual telescope. Very powerful technology to allow new measurements that we haven't been able to do in the past by disaggregating these space assets. And I just want to end with this real quick shameless plug for Goddard, and then I'll be open.
Science and technology are the lifeblood of NASA Goddard. Our people are the brains, the instruments and spacecraft we construct, the bones, the data we analyze, our pulse. So you could say, excellence is in our DNA.
Thank you. So I believe I have time for questions, at least 5 minutes if you still want to go there. If not, any questions?
So we have mics stationed like we did yesterday. If anybody wants to sort of stump the center chief technologist, no, just kidding, or ask a question.
It's pretty
Either
easy.
way.
Any questions?
This certainly is not going to stump you, but that last little transparent card, was that real or is that just a visualization?
There's
created?
video
Okay.
magic.
How far away are you from making that, or is that even something?
That is purely
Okay.
for visual effect in our presentation.
Those are
I
very
will say that kind of in that arena that we're doing a lot of early research on lab on a chip. That's not going to be at a transparent medium, but we really want to be able to have the instrumentation in a real small form so that when we're in situ, we could actually take in the material, we could maybe mix it with some fluids and be able to analyze it in real time. And on top of that, you could have AI system that try to understand what's going on there, or whether we want another measurement. And integrating these emerging technologies that are miniaturized like that down at the chip level, tying it with processing in situ, I think is one of the most remarkable areas that, that's going to pay off big time. We're just beginning to understand this technology, but I think it's an area that is ripe for us to grow in.
Good morning.
Yes, sir.
Excellent presentation. Thank you. For those of us who have kids in high school, looking at colleges and things, obviously all of this is very engineering and physics-centric. But could you comment a little bit on, maybe a little more narrow, about what sort of academic fields Goddard pulls from? A little more criteria that you kind of
Sure.
look for in that. Thank you.
I'd be more than pleased to. Most of the engineers at Goddard are probably electrical engineers, mechanical, aerospace engineers. There are a lot, in the science community, a lot of physicists and specialties at a lower level, and geologists that are doing the planetary work. Regardless, students coming through STEM today really have to have a very broad background, very broad training. You really have to be digital literate, but I think anyone in this generation is. Some of the advice I always give to students are, don't be afraid to take courses outside of your core interests. Take some challenging courses.
That's great to know. Broad. You're not looking for people to get specific and deep early on. Broad-based.
It's good to be specific ultimately. I mean, if you're going to get a PhD, you had to narrow on a specific topic. But I mean, these students these days had to be able to work on a team and work with people and other skills. We really value the diverse skill set that different teams bring, and whether, and that's the STEAM training these days, or trying to broaden that skill set. For the other students, I had to caution them not to be only numerical and be mathematical. They had to have great communication skills, and they had to be able to write and interact with other people. And that's often an area that is a challenge for people that are naturally inclined into these technical areas, but it's an area that is surmountable once they start interacting on teams.
Thank you very much.
I have a question for you.
You need a microphone.
Okay. It's an excellent talk. Thank you very much. My question is for the machine learning. Do you looking for the global machine learning system or subsystem level?
Great question. It's mainly subsystem at this time. I personally believe that the more generalized, bigger ones can be very difficult. We all know the aspirations for generalized intelligence. We use these subsystems. They're great for perceiving and acting on the perception of this, and serving as advisors or actually near real-time decisions. What intelligence systems are lacking now, we need to work on, is the context and how to reason on the context of that. And that's, I think, a challenge that we have for a lot of these intelligent systems. But the commercial sector is investing hardly in this. IBM is investing hardly in this. I was just at a workshop this past week at RTI, an intelligence system, and it's just amazing what's going on out there. How we focus that within our systems at a broader level is a challenge for us, how we code that. But in the area of AI, I think one of the biggest challenges is how do we explain the decision that it made. For us to be able to trust a system and to trust this path, I think we humans, it's a kind of a cultural bias that we want to make sure we understand how it derived that. And once we surmount that, I think they will really explode.
Okay, thank you very much.
You bet. John? Was it John? It was Bob. Robert.
I'm a big fan of the James Webb Space Telescope. How are things going with it?
No, engineer. Can you repeat the question?
So the question is, he's a big fan of James Webb Space Telescope. I do not track that on a regular basis, on a daily basis, weekly basis. I just know this afternoon Dennis is going to have comments, and he could probably give a lot more insights. And I think he was there when we had to overcome some of the most recent technical challenges. But suffice to say, we've been taking steps to prepare.
Hey, Peters. Yo.
Oh,
Dennis.
let Dennis take it. Go.
I can answer that one. The James Webb Space Telescope is doing actually very, very well. It was just shipped back out of the spacecraft element was just shipped out of the clean room where it's had some updates made to it. It is back into the environmental test program. Excellent. We've done integrated tests between the spacecraft element and the telescope. They were all successful. So we are optimistic to getting to our latest advertised launch date of March 2021. So it's actually doing very, very well.
Fabulous. Looking forward to it.
And I can give you lots more detail.
He's going to, too. All right. One more question, sir. And then
Thank you for your insightful presentation this morning. It's good to hear that quantum computing is on your top 4 list. And just a quick question. Just a few miles south of where we are here in Hartford and New Haven, Yale University is doing cutting-edge research, as you're well aware, with quantum computing and qubits. Can you share just a little detail of any collaboration that's currently happening with your Space Institute, NASA in general, collaborating with the Yale researchers? Thank you.
We are in the very early stage of understanding how to program with and have codes for quantum computers. We have a charge to our senior fellows at the Goddard Space Flight Center to understand what the application area is and how we could best exploit this. I say it'd be preliminary for me to say anything that other than we are exploring how to best harness that. We're looking forward to working with our partners to better understand how we're going to be able to do that. All right. With that, enjoy the day. I'm looking forward to this day's events and having further engagement with you during the course of the next 12 hours or so. Thank you.